All right, welcome back to differential equations. Today we're going to be talking, I think, 2.3, which is linear equations. Expand a little bit what I mean by linear in this section. So I want to put a final period on something we talked about in 1.3. We talked about the change of a quantity was proportional to the quantity, okay, equal to a constant of proportionality. And I'll give it an initial value. Okay, I'll say a sub 0, right? When t equals 0, a is equal to m. Okay, so this is a separable equation, isn't it, right? So this is dA, right, over a is equal to k dt. All I did was put the a over and multiply by the k with dt. So we're going to go ahead and integrate on both sides. So we get, right, 1 over u du, 1 over a dA. That's going to be ln a, and that is equal to kt plus c. Right? And now we're going to solve explicitly, so I'm going to go ahead and unlogify this. So we have a is equal to e to the kt plus c, but remember, right, e to the kt is times e to the c. That's what the plus means in the exponent position. If you remember your exponent rules. And e to a constant is just a constant. So we're going to say this is c e to the kt. Okay, so we need two conditions. One to get the c, and the other one to nail down the constant of proportionality. Okay. So here we have a is equal to c e to the kt. Now, when right, t is equal to 0, e to the 0 would be, right, 1. So we have a, actually, what do we say? We said a of 0 is equal to m. So we have m, right, is equal to c, e to the 0, m is equal to c. So we have a is equal to m, e to the kt. We need another thing in here to do this. But sometimes if you're talking about interest rate problems, this is often given to you because, you know, they tell you what the APR is. But you might have to know, like, well, at time 0, there was, like, you know, I don't know, 1,000 mosquitoes, but in 2 weeks, there was 10,000 mosquitoes, and you want to find out how many there's going to be in 2 months. Okay. So that's another condition they would have to tell you. Okay. But that's what gives rise to all of those functions. I don't know if you have to memorize them in college algebra. We changed college algebra a little bit, but that function, right, that's how we got that. Radioactive decay, Q is equal to Q sub 0, e to the kt. In this case, k is less than 0, but you'll figure that out when you plug in the values, and, you know, that's okay. Or population, okay, that one. So if you remember this from college algebra, this is where they came from. They are the solutions to a differential equation, and now you can solve that. Okay, you can solve it when you did Calc 2, actually. So going on to linear equations here. Okay, so one thing I'm going to tell you, our form is y prime plus p of x, so some function of x times y, and this could be a constant. That's okay. Okay, is equal to an f of x. Okay, this is the form you need to have things in order for it to work. Notice the coefficient on your y prime is a 1. Okay, be real careful about that. I remember doing a problem like this and I forgot about that, and there was like an x hanging out over here. And after many pages of doing integrations and integration by parts and everything that could possibly be delightful in a calculus problem, I ended up with about 6 pages, and they were all garbage because I didn't take care of this initial assumption here, this initial condition, and it was the wrong answer. It was absolutely useless. So save yourself the pain, you know, or try it once and see where it gets you, because it's not going to go well with something that's not a 1 in there. Okay, but try to make sure that you have that. Okay. So one thing I'll talk about is an operator. Okay, so I want t as an operator on y, and I'm saying that it's going to be the derivative of y plus the function of y, or function of x times y. Okay, so all an operator is, okay, is, you know how a function, you put in a number and you get a number out? That is what an operator is, except two functions, okay? So an operator takes a function, does something to it, and you get another function out of it, right? If I had like, e to the, 1 over, or dy plus some function here, we would have another function, okay, when I put all this together. So whereas a function takes a number as an input and output you get a number, operators take a function as an input and you get a more interesting function as an output. That's all it is. Okay, so it's just like a meta function that works on functions rather than on numbers. Okay. So what we mean by linear, okay, so we're defining this. This is what t is. This is my operator. Okay. What I'm saying is, for linear, is that t of ay is going to be equal to a times t of y. Okay. So that's one of the conditions we need to see if it's linear. Okay, so just like the function rules, okay, everywhere we see a y, we're going to replace it with an ay. So t of ay is equal to ay tick plus p of x times ay. Right? And since we're taking the derivative of a constant times something, right, a is a constant, so we're going to say this is a times y tick plus a times p of x, y. Okay, because we can just change the order because multiplication cubiques that way. So this is a times y tick plus p of x, y, parentheses, and this is a. And what the heck was t again? T was this thing right here. So this is a times t of y. So this is what we wanted to show. This is what we've shown. So we're good. Okay, that's condition 1. Okay. By the way, if you're in linear algebra right now, you're going to be dealing with something called linear transformations. And this is exactly what you're going to be going through when you have to show something as a linear transformation. Okay, so let's say that there are two other functions, right, like y, okay, and that t of u is equal to u tick plus p of x, right, u, and t of v is equal to v tick plus p of x, v. So the other condition we have to show is that t of u plus v is equal to t of u plus t of v. Okay, so all I'm going to do is I'm going to say, well, t of u plus v is equal to u plus v tick, right? Take the derivative of this thing, of the argument, plus p of x times the argument, u plus v. Okay, so taking the derivative of a sum is very easy, right? We just say that's u tick plus v tick, right? Take the derivative of sine x plus cosine x. That's the derivative of sine x plus the derivative of cosine x. It's not that bad. It's not a product. And then this is just multiplication. So this is u times, or I'll keep it in the right order. Okay. This is p of x times u plus p of x times v. And then we separate them out. And I'm trying to be careful about doing this because I know some of you guys are in college or intermediate algebra, not intermediate, linear algebra. Ugh. And I want to kind of demonstrate, like, if you have to prove this, this is the kind of thing that you're doing. Okay. This is what they want to see when they say prove. And since this was t of u, right? And the whole point of this is like it lines up. Like you would really have to go a stretch and say, I'm not really convinced that this piece is actually equal to this piece. I'm like, no, you don't want to let somebody kind of wander off, like maybe it is and maybe it isn't. See, they're switched. It might not be the same. Like no, you want to make sure these pieces fit exactly into the same block, the same hole, right, as the piece that you started with. Okay, So that's what we have. So t of u plus v is equal to, right, is equal to t of u plus t of v, and you're done. And I know for the people who are like, I don't really care about proofs, this is what they want you to do for a proof. It is in linear algebra classes and sometimes your engineering classes. Okay, math classes, this is what we do. And at the beginning ones, it's like, that seemed kind of obvious. Well, the first ones are obvious. That's fine, but you know, they get harder. Okay, but that's what we mean by linear. Is it's got to hit both of these conditions. Sometimes, right? You say, well, what about t of u plus b of v? Is that equal to a t of u plus b t of v? And yeah, that's the equivalent of doing both condition 1 and condition 2. So you can take a small shortcut by doing this with all the pieces, but if you show this, then it's okay. You've got condition 1 and condition 2. Okay, again, it's going to be for linear algebra. Later on, I will not ask you to do any of this stuff because it's not part of differential equations, although it would be kind of cool if it was. But we're going to learn how to solve these guys, okay, because that's where we're at. All right, let's see here. Great. Sorry about that. There we go. Okay. Yeah. Okay, so let's consider. Okay, and I always love to do this face to face because, well, you'll see in a minute. Don't hold off on scrolling through this or on watching this until we're a little bit more until I've given you the review. Okay, because it's not going to make a lot of sense if you rewatch it without the review. That's going to come in a little bit. So what I say about the first thing, right? We got to make this a coefficient of 1. So we're going to say this is y tick plus 5 over x, right? That's a p of x times y is equal to 7x. Okay, that's what we have. Let's see here. I'm going to multiply by x to the 5th. Okay, so that's going to be x to the 5th y tick plus 5x to the 4th times y is equal to 7x to the 6th. Right? Multiply by x to the 5th. This is what we end up with. And now we're going to make a little guess. Okay, I would like to know if I take the derivative implicitly of x to the 5th y, what do we get? Okay, so this is derivative of the first times the second, so this is x to the 5th tick y plus the first times the derivative of the second, right? That's what the product rule says. So this is 5x to the 4th times y plus x to the 5th y prime. I wonder where I've seen that before. Right there. So what I'm going to claim is that this, right, this term here, that's the derivative of x to the 5th y, and that's equal to 7x to the 6th. Now, if I just take the integrals on both sides, right, this is fundamental thermocalculus, right? We can just undo a derivative and get x to the 5th y is equal to, right? Oh boy, did I come up with a good problem, right? Plus c, okay? So we have x to the 5th y is equal to x to the 7th plus c, and then to finish this off, right, we'll divide by x to the 5th here. So we have y is equal to x to the squared, right? 7 minus 5, okay, plus c x to the negative 5th. That's my answer to that solution, to that equation. Okay. and we could verify. Okay, that's left as an exercise to the reader. All right. So the reveal, right? That we're going to work on that because when we do this in person, um, the question that you should be screaming this question at the screen. You're like, where the heck did you get this x to the fifth? What magic did you do with this? How did you figure this out? I'm going to show you how to do that. Okay. So that's what we're going to work on. Okay. It's what they call integration factor. Okay. Not be the first time I've been called a witch, by the way. So, okay. So we're going to make integration factor. And what we're going to do, okay, is that we're going to figure out what e to the integral of p to the x is. Okay, so I know in calculus we tell you, like, if you got a dx somewhere, dx, we put a dx there, it's not on the baseline, you screwed this up. But integration factor bends that rule a little bit. It's just e to the integral of this function here, and that's what we're going to multiply by. So let's check it out. Okay, when I put this thing in standard form, okay, let's go back to standard form. Y prime plus 5 over x, right? This is y prime plus 5 over x. Y was equal to x to the 6th, was it? 7x to the 6th. Okay, of course it was. Okay, so here's my p of x, right? Right here. So we're going to say e to the integral of 5 over x dx. Okay, and what is that? That's going to be e to the 5 integral 1 over x. That's e to the 5. What is that? It's the natural log of x, isn't it? And remember, there's a right, ln of x to the r was equal to r times natural log of x. Remember that for rules of logarithms? So this is going to be e to the natural log of x to the 5th. And what is e to the natural log of anything? Anything. That's where I got my x to the 5th. It's no sorcery. It's just integration factor. Okay. But the key to doing this is that this first coefficient, when you start, right, this first coefficient here, this has to be a 1. Otherwise, you don't really have your p of x in the right form. You're going to get the wrong integration factor, and nothing's going to work. Okay, so be really careful about that. Right? So let's see here. But yeah, after that, and that unlocks all of your linear equation. I love this when I learned. I was like, wow, that's really cool. I'll do 144 more of those right now. Okay. The first couple of few times you do it, I would recommend to you to actually take care and do the derivative to make sure you're actually getting it right. So I've had a lot of students like, but wait, this here is magic. Like, no, it's not magic, it's integration factor. Okay, we can prove that it actually works. Okay, but let's see here. But let's do a couple more, just regular examples, and maybe we'll get around to like the y in a little bit. Okay, but this is how you solve these. Okay, so what if we do a tame one? Okay, I'll let you guys do a tame one. So let's do a y prime plus y is equal to 2, and I'll give you that y of 0 is equal to 0. Okay, that's our initial condition. Okay, so right, you're trying to sucker us into a problem here, right? I'm like, no, not this time. First one you do should be an easy one. Okay, so this is going to be e to the integral of 1 dx, right? My p of x was 1. Okay, that's where I'm getting that 1 right there. Okay, so that's just e to the x, right? And I'm going to multiply by e to the x on both sides and see what we got. So this is e to the x times y tick plus e to the x times y, that's a plus, okay, is equal to 2 e to the x. Okay, let's go ahead and, typically, at least the book I learned this out of, my integration factor was just called rho. So that's what we abbreviate it as. If you want to abbreviate it as IF for integration factor, that's fine. I usually capitalize these, but I don't think your book has a nifty notation for this. But there we go. What am I looking at here? So yeah, let's take a look. What's the derivative, right, of e to the x times y, right? What's the derivative of the first? Actually, let's change the order. I think more sense that way. This is y e to the x. Derivative of the first, it's y tick, times the second, plus the first, that's y, times the derivative of the second. Hey, that is exactly what we were looking for. So derivative of y e to the x is equal to 2e to the x. We're going to integrate on both sides here, right? Fundamental theorem of calculus, we got y e to the x is equal to 2e to the x. This is why we harped on you for the plus c's all through Calc 1 and Calc 2, is because now it's important. Because this y value, right, is equal to, right, we're going to multiply by e to the negative x here. Cancel that out. We have 2 plus c e to the negative x. Okay? If you forget that c, you're not going to get this term. You're just going to get y equals 2, and that's kind of ridiculous. All right? So realize that that's what we're looking at. But we're not done yet. Don't answer yet. There's more. Y of 0 was equal to 0, right? Y of 0 was equal to 0. So let's plug in, x equals 0. We have 0 equals 2 plus c. And then we have a 1 because e to the 0 is 1. So c was equal to negative 2. So we have y is equal to 2 minus 2 e to the negative x. And that's our function. All right? It's pretty nifty. Let's see. Let's see here. There we go. All right, let's get one that's a little bit craftier. Okay, so we have x, y tick. And by the way, I will automatically give you horrifically crafty, integration-wise, not so bad, okay? But I will really try to mess you up as far as like putting this in a format. You're like, wait a minute, I have to do what now? Yep, that's the point. Okay, so here we have x, y tick, okay, plus y minus 3xy is equal to 0. Okay, so here we have x, y tick, plus, this is going to be like 1 minus 3x here, right? Y is equal to 0. Okay. That's almost the correct form, not quite. And we have y tick plus 1 minus 3x over x. Y equals 0, because we did divide by 0. And I think the last thing we can say about this, if we wanted to, is y tick plus, what did we say here? Did I do? I did it. Okay. This is 1 over x minus 3. Y is equal to 0. Okay. So, integration factor, right? We have rho is equal to e to the integral 1 over x minus 3. Okay, dx. There is a constant in here, and I'll show you what, I'll be careful and show you what happens to the constant. Okay, I'll call my constant here, I'll call it capital A instead of capital C, because C is going to be busy. All right, so here we go. We have rho is equal to e to the natural log of x minus, right, 3x. Yeah. So let's see, that is, what did I do? There we go. That's e to the ln x times e to the negative 3x, right? That's a property of logarithms. E to the natural log x, that was just x. So we have x e to the negative 3x. Here's my integration factor. Okay. Oh, plus, right? We forgot. I was going to be careful, and then I completely blew it off. There's a plus a here too, right? Because I integrated. So plus e to the a. So this is going to be a times. I'm just going to say that e to the a is just a. All right. So that's my integration factor. We're going to multiply this on both sides. So this is a x e to the negative 3x y prime, okay, plus 1 over x minus 3 a times x e to the negative 3x times y, and that is equal to, unfortunately, the right-hand side is just a 0, so everything floats away in the 0. Okay, what am I going to do with this a here that occurs in both terms? Even if it was over here, even if there was something other than a 0 over here, there was like a 1, I'd still have an ax e to the negative 3x, wouldn't I? Right, if that was a 1. What would happen to these a's? They'd all cancel. Okay, so yes, there is a constant of integration that happens here, but because we multiply the answer by both sides, that constant of integration, occurs on all sides, on both sides, and we can just cancel it off. Okay, so it is there, but it's inconsequential. We can introduce it only to cancel it. Okay, so it's not something you have to worry about. Okay, excuse me. So here we go. So we'll go ahead and keep it back to a 0. Okay, and not worry about it. All right, and we'll cancel those. Okay, so let's see. Right, we have x e to the negative 3x y. I'm claiming that this derivative here, right, is this whole thing. Well, let's check. So, oh, easier said than done, right? Oh, why did you have to give us one that had all these terms in it? Like, yeah, I know. So derivative of the first, so what we're going to do is we're going to take our derivative of this piece times the second plus the first x e to the negative 3x times y prime, right? And then we got to take this derivative. Oh, lovely. So derivative of the first, which is just, right, derivative of x is just 1, e to the negative 3x, okay, plus, well, it's going to be minus, but the first, e to the negative 3x times negative 3, right? And then that's going to be y. So that's all of that. Okay, and this is plus x e to the negative 3x y tick. All right, this one pretty much matches this guy over here. We don't have to worry so much about that. But is 1 over x minus 3 x e to the negative x, 3x rather, 3x. Is that equal, right, to e to the negative 3x plus x e to the negative 3x? So if I multiply here, right, the x's cancel and I get x e to the negative 3x. And then here we just have minus 3 x e to the negative 3x. I forgot this negative 3. Okay, put that negative. And despite my sloppiness here, yeah, they're the same thing. So we're pretty good about feeling confident that this here, right, this derivative here is actually these two pieces. So we're going to say the derivative, right, of x e to the negative 3x y is equal to 0. Integrate both sides. Okay, so we get x e to the negative 3x y is equal to, right, integrate a constant. Integrate 0, we get a constant. Okay, so here we have y is equal to, and let's see, how do I want to do this? This is going to be 1, this is going to be c, 1 over x e to the positive 3x. Okay, so there's our fun little solution to that linear differential equation. Okay. All right. Oh, did we have a initial condition here? Back up about a page or 3 when I did this problem. Yeah, y of 0 is equal to 0, right? No, no. Y of 1 was equal to 0. Okay, we had y of 1 was equal to 0. So we have 0 is equal to c, and then we have 1 over 1, e to the 3 times 1, right? And, oh, well, that's a delightful problem. Could have given it anything else over here, and it would have been more interesting because we just have some stuff times c is equal to 0, and c is equal to 0. Such a lovely problem. And there's our answer. Thanks. Thanks a lot. Appreciate that. All right. But, eh, you know, it didn't have to work out that way. We could have had a 1 over here, right? And then c would have been e to the negative 3, or it could have been e, right? Then we had e to the negative 2 or something. Whatever. You gotta love the problems that you work, cure yourself over, and then at the end, you got nothing. Okay. Let's see here. A couple of word problems, but I realized that we do word problems in a different section in this book, so we're not going to touch those. And let's see. Okay, we'll do one more, and this one was we'll go back to the idea that these could be terrible. It isn't. It's not really that bad. We'll do y tick. Okay, so you know something's up because you didn't get a coefficient here. Okay, y times cotangent of x is equal to cosine of x. What is this? So my integration factor, right? Because we're in the right format. Right? I could write cotangent to begin with. We're in the right format. So this is e to the integral of cotangent x. Oh, how delightful is that? Okay. What's cotangent? Isn't it like cosine x over sine x? Right? By the way, in the old days, when typesetting wasn't quite so good, we used exp for e. So we used to have that, and this helped you keep everything on one line rather than subscripting everything or superscripting everything and having to deal with it. So we would say something like let u is equal to sine x, du is equal to cosine x. So we're going to end up with e to the integral of 1 over u du, okay, which is going to be e to the natural log of u, natural log of sine x. Okay, is that what we're doing? Yeah, I think it is. And that's just e to the natural log of something is something. That's just sine x, isn't it? So that's my integration factor, sine x. So back up here, we've got sine x times y tick plus y times, well, we have sine x here times cotangent. Cotangent was cosine x over sine x, wasn't it? And this is going to be equal to sine x cosine x, right? So some stuff happens, right? So here we have sine x times y tick plus y times cosine x, and that is equal to, oh man, I could not have helped for a better problem. Okay, this is a little rant of sometimes grading CNN is really rough. I mean, I went to tech, so everybody had like the same Calc 1 teacher, and they did everything exactly the same way. And then everybody had pretty much the same Calc 2 teacher, so everybody integrated very consistently, and you guys don't. Okay, which is fine, but you know, it's funny that you know, I watch some of you guys integrate, and it's like the people who taught you how to do this were just cruel. Okay, so this is going to be sine or y times sine x. Okay, and we're taking that as a derivative. Let's check. Derivative of the first times the second plus the first times the derivative of the second. Hey, that matches up pretty well. So we're good. Okay, so we have the derivative of y times sine x. And then on the other side, we've got sine x cosine x. Okay, here's what I mean by, sometimes it's a little frustrating. This is x sine x when I integrate. Now, integrating this, like I watch people do this, and you do a 1 and a 1/2, or you do a 1/2 here and a 2 here to turn this thing into a sine 2x and then integrate that. So like that is technically correct. I really didn't understand why let u equals sine x, du equals cosine x, integrate u, right? Let's get rid of this stuff. We don't need that. Du, so y sine x was equal to 1/2 u squared sine squared x plus c, and then y is equal to 1/2 sine x, because we're divided by a sine x, plus a c times cosecant x, 1 over sine x. Okay, that's the other way is just as correct. Okay, but whenever I saw sine x cosine x, the automatic move from pretty much everybody in my cohort at Tech, this was the move to make to integrate it. And the first time I saw this, I'm like, well, yeah, technically it's correct. I mean, it might be easier. I'm not gonna, you know, I'm not gonna fault people for doing that. It is the right way to. It is a right way to do it. So, you know, I'm not gonna, you know, you're getting the right answer consistently. I got no complaints. But it was just really shocking to kind of see that the first time I ever did. But yeah, there's our integration factor. So it doesn't always have to be an e to the something. Okay, you're not always going to get an e to the x integration factor. Sometimes you get sine, or you'll get a polynomial like we did in the first one. Okay, so I'm going to stop us there as far as linear systems or linear equations go, and I will meet you on the other side for, I think we're doing substitutions or something, but we'll see. Okay, thank you.